Okay, section 3 of chapter 26 deals with the topic of electricity in the home. So far we've dealt with individual single circuits which have a power supply and a resistor and maybe a few other items, and we consider them in isolation. But in a home, all circuits, all devices that are plugged into the wall and therefore plugged into the power supply that is supplied by the power company need to have a common reference point. They are all tied together with a common terminal which is called ground. And the ground is actually the earth. The earth itself is a conductor, and so all houses have a line that goes into the ground and therefore grounds the entire home, so that that can be used as a common reference point for all circuits. In practice, we could call the potential of the earth 0 volts. We have the freedom to do that, even though the earth is actually slightly negatively charged. However, we can call it 0 volts because we have the freedom to do that with electric potential, much as we do for potential energy. The outlets in a typical home are connected in parallel. Outlets are usually distributed throughout the house in the walls, and that's the point at which you plug in to get power for the various devices in your home. And you're quite familiar with this, I'm sure. If you look at an electrical outlet, one of these outlets right here, there are 3 prongs typically. In older homes, sometimes there are only 2 prongs per plug, but in modern homes, there is a very clear ground connection. The terminal right here on the bottom has a direct connection to ground. And then there are 2 plug-in tabs, or plug-in terminals. And the larger of the 2 is called neutral. It's actually grounded. We call it the neutral side. The other side, the smaller of the 2 plugs, is called hot, or the hot side. Each outlet has these 2 slots, one connected to each side. And notice in this particular case, here's the supply coming from the power company, and then there is what's called a circuit breaker, which is something that will open and therefore open the house open the connection to the house in case the current drawn by various devices in the house exceeds a certain value. A particular outlet typically has a 15 amp circuit breaker connected to it, or a few outlets might all have a 15 amp circuit breaker connected, as is shown in this diagram. And that means that if any one of these or all 3 of these draw more than 15 amps of power from the power company, this switch automatically opens up, therefore disconnecting the power outlets from the power supply. And that's done for safety concerns, because if the current does rise too high, the I²R losses can become significant, and the heat produced can become significant, causing a possible fire. So all outlets are connected to a circuit breaker, all of which are located in a circuit breaker panel. Any individual circuit breaker either feeds one outlet or a few outlets, or one of a few devices, for example, a light in the ceiling with a switch on the wall. There are several circuit breakers in that panel, and the total current coming into the house can be something like 120 amps, but each individual collection of circuits has its own circuit breaker to make sure that no circuit draws more current than it should for safety reasons. Each one of these plugs, you'll notice, is connected to a resistor, which is symbolic for a device. It could be a light, it could be a fan, it could be a microwave oven, it could be a computer, it could be a number of things that are plugged into these. And this one in particular is opened with a switch. As soon as the switch is closed, this circuit will be complete, and the outlet can deliver power to the device plugged into it. When we insert the plug into the outlet, the prongs connect to the 2 terminals of the electric supply, and by doing so, when you plug in a device, you are plugging in, here's a device right here, you're plugging that into the outlet and therefore completing the circuit. Without that device connected, we have no complete circuit. The ground or neutral and hot side are not connected to one another, and so no current will flow until a device is plugged into that outlet. So all outlets are grounded, and all outlets are connected to some kind of circuit breaker for protection. Switches, such as this one right here, are usually located either in the wall for a light switch, for example, or in the device itself, an on-off switch in the case of a microwave oven, for example. The reason that electrical outlets are connected in parallel is so that one can be used while the others are not being used. If they were all in series, then it would require that they all have their switches closed so that current would flow through the entire circuit. But connected in parallel allows us to operate devices independently of one another. If multiple outlets are used, then the total current in the circuit increases. If I plug in many things and use them, we're going to have an example of this a little later in this section, the current increases, and so it's important that the current not increase above a certain value. And the wires themselves are not ideal. They have small resistances and can heat up and cause a fire if there's too much current. That's the reason, like we just said, for circuit breakers, which limits the current in each circuit. They're devices that simply trip open if the current exceeds a certain value. Now, the kilowatt hour is actually a unit of energy for electrical power that the companies use to measure the usage for a particular home. We talked about this in class briefly recently, but a kilowatt hour is a unit for energy much the same as a joule is. We know that watt is a unit of power, and kilowatt is therefore 1,000 watts. But if you multiply power by time, a kilowatt times an hour, then you actually end up with unit, because you'll recall that power is energy divided by time. How much energy did I expend, and how much time did it take me to expend that energy? So if we multiply the power times time, we end up with energy. So the unit of energy that we're concerned with here is the kilowatt hour, and that's the unit that is used to judge how much to charge a customer based on how much energy they've used. The conversion between kilowatt hour and joules is done as follows. 1 kilowatt hour is 1,000 watts times 3,600 seconds, which is an hour, and that gives us 3.6 times 10 to the 6 joules, or 3.6 megajoules. So 1 kilowatt hour is about 3.6 million joules. And your monthly bill, of course, many of you are not receiving monthly bills yet. Some of you might be, but someday you may own or rent a home in which you are responsible for the power bill. And your monthly electric bill specifies the number of kilowatt hours you used in the previous month. It doesn't matter so much how much power you're using, but the sum of all that power over time gives you the amount of energy that you've used. And the amount of energy that the electric company delivered to you that's been transformed into all the various things inside your home eventually end up as heat. Let's compute the cost of electrical energy. A typical space heater, which many people are using during this winter season to heat up a room, the typical electric space heater draws an RMS current of approximately 12.5 amps on its highest setting. This is not unlike what a typical hairdryer might consume as well. If the electricity costs 12 cents per kilowatt hour, which is an approximate national average, the question can be asked, how much does it cost to run the heater for 2 hours? So 2 hours is 3,600 times 2 seconds, or 7,200 seconds. And we know enough to figure that out. The power, as we've learned earlier, is the RMS voltage times the RMS current. The RMS voltage in a house is 120 volts. And for an RMS current of 12.5 amps, which is about how much current this space heater is using, we can take the product of those two and find that it uses about 1.5 kilowatts. That is the energy per time that it's using, 1.5 kilowatts. In 2 hours, we can multiply this by 2 hours. 1.5 kilowatts times 2 hours, which is 1.5 kilowatts times 7,200 seconds. We don't need seconds in this case because a kilowatt hour is already the convenient unit. So we multiply 1.5 kilowatts times 2 hours and we get 3.0 kilowatt hours. At 12 cents per kilowatt hour, that means that we have consumed about 36 cents of electrical energy. Okay, so running a space heater in a room for about 2 hours costs approximately 36 cents. Okay, let's consider an example problem. The following devices are plugged into outlets on the same 120 volt circuit in a house. So in other words, they're connected to the same circuit breaker. The circuit is protected by a 15 amp circuit breaker, and the question is, does the circuit breaker blow, or does it trip in order to isolate these devices from electrical power? A typical computer, at least a desktop computer, which are more rare these days than laptops, a typical computer will use about 250 watts of power. The heater, a heater might use about 900 watts of power, a lamp about 100 watts, and a stereo about 120. If all of these are operating together, we can find if they actually will trip the circuit breaker. The power is equal to the voltage times the current. And the power that is maximum, the maximum power allowed by the circuit breaker is going to be 120 volts times the maximum current. If it's a 15 amp circuit breaker, that means the maximum that it will allow to flow through it to those devices is about 15 amps. So the maximum power we can draw is 1800 watts on this particular circuit, corresponding to a few outlets that are connected to a common circuit breaker. If we add up the power that is used by the computer, the heater, the lamp, and the stereo, we end up with 1370 watts, which is below the 800 watt limit, and therefore these devices will not cause the circuit breaker to blow.